All right, welcome back to System Software. So today we are going to finish up the last syscall API that we're going to use for our processes. That's the pipe syscall, and how we can use that together to actually do what we did on the command line. Use this for inter-process communication. So before we begin, questions from last time. We looked at redirection last time, how we actually implement that using kernel calls. Questions on that? Questions on the FS project? I see there's a couple pending on EdStem. I haven't gotten to. I got to a couple of them. I'll get to those today. But other questions on class last time? Okay, let's go over the homework. All right, so first question is, which files comprise standard I/O? How many are there and what are they? Three? Okay, and what are they? What are they called? Yeah, input, output, standard error. All right, good. Write a bash command that uses grep to find lines matching hello from standard in, redirected from a file called my.in. So it's a lot of words to say something that is pretty simple to do on the command line. So it says use grep. So how do we use grep to match lines that match hello? Yeah, grep space hello. So that will run grep, and grep will take, without any other arguments, it'll read from standard in and write to standard out. So if I just hit enter now, it'll wait hanging. Why is it hanging? What's it waiting for? What's that? It doesn't know where to what? Well, what is the input right now? The terminal, right? Why is it the terminal? Yeah, because grep works from standard in. And whatever the standard in is, so who set terminal to be the standard in for grep? Bash. Yeah, so bash is running now with the terminal as standard in and standard out for its process. It invoked grep using fork and exec, and it just gave it the same standard input, output, and error that the terminal bash has. And so that's why it's sitting here waiting on an open file, which is our terminal. And and we can type into the terminal, and that will be processed by grep. You can see grep echoed any lines that match this substring hello. Okay, but the question was, how do you run it? Well, using standard in still, but instead having standard in redirected from a file called my.in. How can we write that in bash terminal? So that I see hand gestures, that's new, I haven't seen that. Hand gestures for telling bash to use this file for standard in instead. So let me actually make this file, and I'm going to use redirection to do this as well. So cat will run, what does cat do? Reads from standard in and writes to standard out. The exact same text. I mean, it does other things, but without any arguments, this is what it does. So I'm going to use this, take advantage of the fact that terminal is standard in, and write some lines here. So now I've got this file my.in, and I use the angle bracket, left angle bracket, which looks like an arrow, to redirect standard in to grep from this file my.in. And what should we expect to see? How many lines should be printed out? 2 lines, and yeah, that's exactly what we see. So that's question 2. Questions on this? Okay, why doesn't a program have to open the standard out file? As we saw when you write a C program, you can just call printf, and printf writes to standard out. So why doesn't a program have to open that file before it writes to it? Yeah, and who opens it? In our case here, when we ran grep, bash. Bash did it, right? So bash called fork and exec, and before it called exec, it set, or actually just copied the standard I/O from bash. Didn't even have to open it. But because the processes are copied. Okay, what syscall duplicates file descriptors? I think I heard it. Dupe, right? There's a series of syscalls with dupe. There's dupe2, dupe2, and dupe3. We looked at dupe2 and dupe2 last time. this is how we can duplicate file descriptors. And just as a little, well, yeah. So why might you want to use this syscall? What can this be useful for? What did we see last time? How did we use it last time? Redirection, yeah. It's for implementing everything we're talking about. That's what Bash does. Bash uses dupe for redirection. So remember, it doesn't create a new file. It doesn't open a new file. It just copies in the open file table, the file descriptor table, it just copies an entry. So it's like a pointer to an open file. So now there are two file descriptors that point to the same open file. And why would you want to duplicate that? Well, redirection is one use for doing this. Okay, and then write a snippet of code that redirects a process's standard out to a file called my.out. So this is really just taken from the lecture. So you could just look at let's see, redirecting a child process's I/O. That's what I said, right? Well, so I didn't specify. It didn't have to be you didn't have to invoke a program or anything, but here's an example. This example is here. So this is an example of, what did I say? Standard out. So yeah, this is an example of it, this code here. That was in class. So it opens a file. Here it's opening the file from arg1, but you could just change this to be a file called my.out, and then fork a new process, redirect it, and voila. Yeah, that's really all I was asking for here, just the code from class. Questions on that? Question on the code from class? Okay. All right, let's do attendance. All right, so today we're going to look at pipes, how pipes are implemented. So just to remind you, an example of using a pipe, let's say we use ls to list out all the files in this directory, usr include. Then we can, instead of having to redirect this to a file to save it, we can immediately pipe or pass the output of ls to another program like grep. And what Bash will do, and using the system, it'll run both processes and basically do two redirections, redirect this ls to grep. But without any file, where does that file come from? Well, that's called a pipe. And then, let's actually go over what pipes are, and I'll show coding examples. But first, let's go back to the notion of a process. Remember, what's a process? A process is a running program. But what does this abstraction provide? So what is the kind of guarantee that the operating system gives you, the programmer, when you use it to give you a process? So normally, if you just take a machine, like something with like an x86 processor and a motherboard, you don't need an operating system to use that device. If you can get your program loaded into memory and you can kick off the processor, you'll have a machine that just runs one program and then stops when your program is done. So what does the process abstraction give you in the operating system kernel? Yeah. Oh, thanks for asking me. Yes, I am. And don't hesitate to remind me. I am recording. So I should figure out a way so you can see it on the screen. I could just leave this up, I guess, but that might be a little onerous. Let's see if this gets in the way. All right, so what does the process abstraction provide for? Yeah, it provides you multiprocessability, because now that you're not actually in total control of the hardware, the operating system can switch between processes on its own. And so how does the operating system do that? How is it able to switch between multiple running programs? Yeah.
Just might be limited amount of clock cycles for each program, rapidly switching between them.
Yeah, so it rapidly switches between them. But if that program's running and then you just stop running it, how is it able to restart the program? If you remember, we maybe only went over this very briefly. It suspends it, but what does it do to suspend? How does it suspend it? Didn't remember mechanism? Yeah.
Stores all the program's details in memory, and then it just pulls back up.
It stores all the program state, details or state. So it stores the processor state. It stores all the open files, all the information about that running program that goes beyond just the code. So everything you need to freeze or unfreeze that program. So you may have a car, but if you want to sort of freeze that car driving on the road, you need to know how fast it's going, you need to know its location on Earth. So the car has an engine that allows it to move, but a moving car has a place and a location and a speed. Yeah.
Does it store everything needed, or does it store like the simplest amount of terms, like very simplest amount of details needed so that when it reopens?
That's a good way of saying it. I mean, it's kind of both. It stores everything that's needed in order to restart it. Otherwise, it couldn't faithfully restart it.
Yeah.
But in implementation, it just the engineers enumerate all of the information needed in order to resume that program. So it's just kind of both. I mean, in a sense, it's both. But what it also guarantees is that you have isolated memory. So this abstraction gives you the illusion that you have the exclusive access to the processor, but it also gives you the illusion that you have exclusive access to memory as well. And it does that by just allocating different chunks of memory to each process. But the problem with that is it means that no other process can read each other's memory, and that's what you want. You don't want your browser to be reading, writing to like the video game you're running or to your, bank account software. And so that isolation gives you this kind of security benefit as well. But what if you want programs to communicate with each other? So in this case, we wanted ls and grep to communicate with each other. We didn't want to keep them entirely isolated. We wanted them to communicate with each other. And so this is what pipes provide. Pipes provide one mechanism for so-called inter-process communication, how two processes can communicate with each other. And standard I/O is what enables piping to work. So each process is given this standard input, output, and error. Just a little review, why did the Unix designers use standard I/O? Why does it give each process the same set of open files, or standardized set? Yeah.
So if you run it on a different system, it's still expecting the same input and output because of the standard.
Yeah, they're no matter whether you run the program with files being used as input or output, whether it's an Ethernet device, whether it's USB or serial port, the programmer doesn't have to care where that I/O is coming from. It can just use standard I/O and be guaranteed that the system will open those devices or files for it. So it abstracts away those I/O decisions from the programmer. And so who sets the standard I/O for a process? Well, Unix is the operating system, this is the kernel, and the larger system. But when a new process is created, which process or what decides what the standard I/O will be for that process? The parent, the parent. Good, yeah. So the OS enables it by providing these system calls for creating processes and changing the files, the I/Os for that. But like we saw last time, when we wanted to do redirection, we created a process with fork, and then before we actually executed a new program, we could alter what standard I/O would be for that. We could just close the old standard I/O files and open them with new files. That's what dupe allowed us to do. We could open a file and then use dupe to overwrite what standard out or standard out in was. Okay, so questions on this, these kind of basics of processes, standard I/O. Okay, and so as I kind of motivated with talking about processes, these processes are isolated. The hardware, it's as if each process has its own exclusive access to the hardware, and it's the operating system that switches between them, maintains separation of memory and other state. And so pipes are how you can communicate between two processes. So there's an example we already saw an example of this. So here's how it works, kind of conceptually. Let me get my diagram here. So there's a system call called pipe, which when you create it, it creates, usually in memory, an in-memory buffer that stores information, and it creates two files, or at least two file descriptors. It creates an input and an output file descriptor. So you get two new file descriptors. And both of them read and write effectively to the same place. It's effectively a file, because a file descriptor has an open file, but you can think of the kernel as creating this new open file and then giving two file descriptors, one to write to the file and one to read from it. So whatever data I put into this file descriptor, I can read it from that file descriptor. And it's FIFO, first in, first out, like a queue. Questions on that concept? So that's all a pipe does. So you have a system call, just like dupe fork. You have a system call, and the kernel will manage how this actually works under the hood. For you, the programmer, you get two file descriptors, you write into one, you can read from the other. So that's why it's called a pipe, right? Because like water flows through, you go into one, you put water into one end of a pipe, and it'll come out the other end. So that's pipe. So just to extend this diagram a bit, if I have this instruction here, and might as well run this, since this is my running example. So find user bin. So what'll find user bin do? What'll that program do with that argument? Yeah, it'll list all the files here. And grep, as we saw before, will only match lines that have the substring zip in it. So what'll the output be here? Yeah, all the programs that have the word zip in it. So here's what that execution looks like. Yeah.
How come they need to put like a quotation mark, right? Or is a quotation looking for a string inside the file?
Quotes, it's kind of a little annoying and complicated how Bash processes quotes, but quotes are used to group together stuff, say with spaces in them, and then you have to like escape them if you actually want to match it. It's very annoying dealing with like quotes and escaping, but it's not a super important detail, but they're used in Bash to group together stuff with spaces as a single argument. And there's some other really annoying details of it, but yeah, if you wanted to search for a quote, you'd have to escape it, just like in C with the backslash character. All right, so there's our execution of this program. So conceptually, find runs, and then its output, instead of going to the terminal, it goes into this pipe, and grep reads from this pipe. And that's how piping works. That's how we have this early, simple form of inter-process communication. We can have two processes run. They run effectively in parallel. And through a pipe, they can communicate with each other. They can send information back and forth if they create new pipes with each other. Yeah? Yes, yeah, you can absolutely use multiple pipes. And I think very, very prescient, that was my next example, is multiple pipes. So absolutely. So you can have, I think, an unlimited number of pipes. I don't think Bash limits the number of pipes. It may be limited by the number of processes you have. But here's an example of, well, also, first of all, questions on the single pipe. Questions on this example. And so this is where standard I/O becomes really handy, because find was written by the programmer to only use standard I/O, or not only, but by default to use standard I/O. We don't have to reprogram find at all to make this inter-process communication possible. All we have to do, all Bash has to do, is use pipe and redirect find and grep to and from that pipe. And voila, with the exact same program, we can now have this larger program kind of put together like Lego blocks to make a bigger application. So it's kind of the Unix philosophy, is you have small, simple programs that have one well-defined task that use standard I/O. And then with pipes, we can connect these together like Lego blocks and build a larger, more complicated application without writing any C code at all. Yeah?
Is it guaranteed that find will always like run first? Rep tries to read from the pipe, but find doesn't do it.
Okay, so that's a good, subtle question. And I'll actually illustrate an example of this. So it doesn't have to run first, and it doesn't. I don't think it's guaranteed to. It probably will because of the implementation, but it doesn't have to. Because just like when we, on the command line, if we just run grep on the command line, grep is waiting for input. So this is more for an OS class, but this is called blocking I/O. So these read and write operations that we see in the syscalls, these are called blocking I/O. That means when you call them, the kernel will pause your program until that input is available to your program. So when you call read, your program, it's like a function call. It is a function call, but it's a synchronous function call. So when you call read, it goes into the kernel. If the kernel has that data available, it'll immediately return. But if it doesn't, then your program is just waiting for that input to happen. And this is a kind of an important technique for performance in operating systems because I/O is typically slower than the CPU. So the fact that we have multi-process already, the kernel can cleverly schedule your program so that stuff that's waiting for I/O can be frozen for a while stuff that is CPU bound will run, and then your whole system will appear to be faster. But no, these programs don't have to be run in any order because for the same reason that this program, grep, is waiting for my terminal input, as long as there's an open file and grep is trying to read it, it will be stopped waiting for data to come through that file, whatever the file is. So this could be a serial port or a USB port on some thermometer. If that thermometer takes a few seconds to send a reading back, your program will be blocked or paused waiting for that input to come into the program. So no, it doesn't actually matter. As long as this pipe is created and grep is reading from that open file, it will pause and wait for that data to come in. So you write the read command and you ask the kernel for, say, 10 bytes of data. It will try to satisfy 10 bytes of data for you. Now, there might be reasons why it gets interrupted and has to stop and return to you. But typically, the kernel will just block. It'll just pause you and run other stuff while that I/O is being handled. So yeah, good, subtle question. We'll see an example of where, especially when you write your own shell processor, which you're going to do starting next week, this can be a reason why your program hangs. So if you don't close that input, then your program might be hanging, continuing to wait for input. All right, good question. So any other questions on this single pipe? So a pipe is really just a file, a special file in memory, and the kernel gives you an input file descriptor and an output file descriptor, so that any data you write into the input file descriptor will be available to whatever process is reading from the output file descriptor. Okay. So let's see just an example of using multiple pipes. So yes, you can absolutely do multiple pipes. So in this example, we'll have 2 calls to pipe, and the kernel will create 2 buffers. So the data from find will go into this pipe. grep will read data from that pipe, from the output file descriptor. And grep standard out will also, in this case, will write to this new pipe here. And the WC program will read from that pipe. So you can see how you can start building up large, complex applications by just using simple programs and pipes, inter-process communication between them. Questions on this? Okay, so that's pipe at kind of a high level. Where is? Oh yeah, okay. So the syscall for this, appropriately, is pipe. And here's the reference for it. Oops, I'm still running here. Let me also open up this diagram here. Oops. So just to point out, I can't remember if I assigned this for today or yesterday or last time. Pipes. Yeah, so it's read for tonight. So if you read the textbook, this will go over this more, but it has similar diagrams. So this is the pipe diagram, and it goes into more detail and code examples. So read over that. That's the assigned reading for tonight. Okay, so let's take a look at the documentation for pipe. Because it's a little, it's a very C-like way of implementing stuff. All right, so we've got pipe. It takes an array of size 2. How does that get passed in C? How do arrays get passed in C without any other features being used? If you create an array and then you pass it to a function, what's getting passed? What's that? The address, good, yeah, exactly. It's passing, because what are arrays in C? Arrays are really just pointers under the hood. And so if you pass an array, it's just passing the address to that array. So good. So pipe takes the address of an array. Does pipe create the array? Does it allocate space for the array? No. If you're just passing an address, that means the array must already have been created. So let's see the description here. It creates a pipe, a unidirectional data channel that can be used for inter-process communication, exactly what we talked about. The array pipe FD is used to return 2 file descriptors referring to the ends of the pipe. This always confuses me, so I always have to look at the documentation. But the first element, pipe FD0, refers to the read end of the pipe. That feels backwards to me. I don't know why it's like that, but the first element is the read end of the pipe. The second element is the write end of the pipe. And so it says just what we talked about, data written to the right end of the pipe is buffered by the kernel until it is read from the read end of the pipe. So I was just describing exactly what we just talked about. And then let's see its return value. Just like lots of other syscalls, on success, 0 is returned, on error, -1 is returned, error number is set, etc. Okay, so questions on the API documentation? So remember, be sure to refer to this. This is included in all on Eustace and any most Unix installations you'll have. If you forget, what the interface looks like, if you forget whether it's 0 is the read or write end or 1 is the read write end, use the documentation to quickly refresh yourself. Questions on this? Questions on the API documentation? Okay, hopefully pretty familiar by now with syscalls to some degree. All right, so let's look at a code example of actually using pipe. Make sure this actually works. Oh yeah, I have sleeps in there. All right. So let me go over the code first. So just as a refresher, what does fork do? So we call fork in here. What does fork do? Creates a new process. Does it run a program? Does it run a new program? No, it just forks a new process, duplicates the process. And how can we tell whether we're in the parent process or the child process? The return value of fork, right? So this is kind of like template code here. If you just look at the switch statement and the cases, this is like a template for using fork. You call a fork, and then you check -1 is an error, 0 it's the child, otherwise it's the parent. Questions on that? We looked at that a couple times in the last week. Questions on fork? Okay, hopefully that's not won't trip you up too much. But okay, so in this example, all we're going to do is we're going to create one of these pipes. Let me diagram this. This program is going to create a pipe, and it's the same process. It starts out as the same process. So we have our pipe program here. And then we're going to fork a new process. Now, because fork doesn't actually run any new programs, it's just going to duplicate the process. All of its state, exactly where it was running, all of its memory state, all of its open files, which includes this pipe. So we call pipe, we get this two new file descriptors and this in-memory buffer, this kernel buffer. We call fork, and then we're gonna, which program is it? So we're gonna read from the child and write from the parent. So we're gonna redirect, actually we're not even gonna redirect, we're just gonna write data into the write end and read data from the read end. So we call pipe. So now we've got two new file descriptors and this pipe, this in-memory buffer. We then call fork to create a new process. And one process, the parent is going to write into the pipe, and the child process is going to read from the pipe. Questions about this setup? So all we're going to do is going to create a pipe, then we're going to create a new process, and write data between those two processes. That's what this code example is going to do. Questions before we go on? Okay. All right, so here's what the code looks like. I just wrote a little program that'll read in an argument, and that's the message that's going to be passed between the two processes. So here's our call to pipe. Any questions about the -1 or p error? Questions about that? Hopefully that's familiar right now. This is just like error checking. So we call pipe, and once we call pipe, we have this new in-memory kernel buffer and two file descriptors. Oh yeah, so notice here, I initialized a new array, and there's no pointer. I didn't write a pointer here. I just said, give me an array of size 2. This is allocated for us by the function, right? We don't have to call malloc on this. It's not pipefd is a pointer, but if you say, in C, if you say the size of that array, it's going to allocate that for you already on the stack, which we'll learn about in a month or so. But questions on that? So we made a new array. This is allocated as a function local variable, and we pass the address of that array, because remember, the array variable is really just an address in C. We pass that address to the pipe syscall, and it's going to give us two file descriptors. Confusingly, the read end is, as I always forget, so pipe 0 refers to the read end, pipe fd1 refers to the write end. So this is going to be pipe fd0 is going to be the read end, and pipe fd1 is going to be the write end. Just to keep track of that, because I always forget. And now we're going to fork. And so this is the exact same template of creating a new process that we saw in the last lecture and the lecture before that on process creation. Case 0, that's going to be the code that runs in the child process. And default, that's going to be the code that runs in the parent process. Questions about that? So remember, if you don't call exec, the processes are running the same program. And since fork returns 0 for the child and non-0 for the parent, we can run different code for the parent and child process, even if we don't actually exec a new program. Questions so far on this? Okay, so in the parent, what we're going to do is we're going to write to pipe fd1. So remember, pipe fd1 is the write end. We're going to write data into that pipe, and in the child, we're going to read data from the pipe. Okay, so let's look at all the extra stuff here. All right. So when we called pipe here, did we call pipe before or after we fork? Before, right? Before. And pipe creates new file descriptors, pointing, these are open files. They're pointing to this kernel in-memory buffer. That's why, remember, the file abstraction does not mean storage on disk storage necessarily. The file abstraction could be anything behind it. So in this case, the pipe file descriptors are backed by this in-memory buffer. You know, it could be an Ethernet device, could be USB. In this case, the pipe file is an in-memory buffer that the kernel maintains. But regardless of that implementation, we just get file descriptors back. So we get 2 file descriptors here. When we call fork, which process has the pipe file descriptors? The child or the parent? It's a little trick question. It's both. Because remember, when you duplicate a process, everything is duplicated, including all the open files. That's how we're able to do redirection and copying, you know, standard out and standard in. So when you call fork, all file descriptors are copied. So that means both the parent and the child have pipe FD1 and 0 in their open file table. They're both open for both of these processes. So just to be organized about this, because the parent is not going to read from the pipe, it's only going to write from the pipe, we can close the read end. Does this close pipe FD0 in the child? No, right? Because this is code that's running in a new process. It has its own open file. So if we close the read end in the parent, it's still open in the child. Because these 2 snippets of code, this case and this case, these are now running as 2 separate processes with their own state, their own open files. And same thing in the child, we close the right end of the pipe from the child. I always have to remember this. Pipe FD1, that's the right end. Questions on that so far? I'm going to take out the sleep. All right, so in the in the parent, what we do is we close that read end, and we write whatever argv1 was. We just write the message that we had. Actually, I think I had a variable for this. Let me use the variable for this. We write that message to the pipe. And then finally, we close that file descriptor. And I'll show you here that if you don't close that, the child process will be, you know, waiting for that file to close. So we close the read end, write to the right end, and then close the right end of the pipe, and that's it. So it'll wait. I'll go over this in a little bit. It'll wait for the child process to finish. That's all wait does. Then in the child, we close the right end of the pipe because we're not going to use it. The parent uses it, and then we read from the read end. So this is just a way to read, keep reading. So this will read 1 byte at a time. So remember the read syscall. It's here's the file descriptor. This is the buffer to store into. This is just a single character. And then we read 1 byte at a time from that buffer. We take each byte that we read in and we write it to whatever standard out is. We haven't done any redirection here of standard out or in or anything. So this is just like printf. This is just going to write that byte to the output. Questions on this code? Questions on this code so far? Okay. All right. So let's see it run, and then I just write a new line just to make it so it looks good on the bash shell. We close this read end for kind of good practice to close your files, although they'll be closed anyway, and then we exit. All right. So let's see this program running. Let me take these sleeps out for now. Okay, so you put a message in like hello, and not very impressive looking, right? So it just looks like if you had a program that printed out hello world. That's why I had these sleeps in here so you could see the multiple processes. So I'm just going to sleep before I read in the child and sleep after I write in the parent. So this way we can see all the processes that get created. So I'm going to run this in the background. And you can see we've got 2 instances of this program pipe. We ran it once, but remember it calls fork, so it creates a new process. There was our hello being printed out. But that just shows you that, there are actually 2 processes being run here. So let me run this again. And so you can see the parent is still running here. So this is the parent, 4-4. This is the child, 4-5. Because I slept in the parent after waiting for the child to finish, the parent was still running, even though the child finished. But anyway, that's just to show you that there really are 2 processes running here. So yeah, that's it. We've successfully used a pipe to communicate between 2 processes. Questions on this? Yeah.
So as long as the right end closes, the child will close as well, but the parent will never automatically close.
So the parent, without this wait, let me show a couple of these differences here. So I'm going to take out these sleeps because they're too long. So here's our pipe program running quickly. All right, so if we didn't call wait, then the parent would just quit immediately. The parent would just quit. So if we didn't call wait, let's say the child ran slowly. So we put a sleep in the child. Let me see if I can actually show this. Oops. Yeah, you can't see that that's the child. Let me do it this way. Okay, so 4-7 and 4-8 are the parent and the child. Oh, it's quitting anyway. All right, it's gonna be hard to show that. But if you don't sleep, then, or if you don't wait, then the parent will just quit immediately.
And now close the read as well.
The read is being closed here.
But what I'm saying.
Or sorry, the write is being closed here. Oh, well, it won't close the. All right, I'm confusing myself here. Okay, so regardless of the pipe, if you invoke a child, and then the parent just quits, that child will just continue running. The child will continue running, regardless of the pipe. So I was trying to show this here. I was trying to be clever and show this on the fly. I think I have to do something a little more sneaky to actually do this. Yeah, I'd have to show it this way. Yeah, so you can see this is 4-4. This is the process ID of the parent. 4-5 is the process ID of the child. So you can see here, the child is running alone without the parent. The parent is already finished here, and the child process is running by itself. So that was just a clever way to show that. Don't worry about that too much, just to kind of convince you that that's what's happening. Okay, so that's one point. That's one question, one separate point, which is that once you invoke a child, the parent does not have to stick around. But you can use wait in order to have the parent pause, suspend until a child process exits. Okay, so the second point is the child process. The child process is sitting here waiting to read on this pipe. And so and it's, while it's doing this over and over and over. And remember, these read and write operation will wait for the IO to finish. So in this case, read is going to wait for the IO to finish. If I never close the pipe, if I leave the pipe open on the right end, then the child process will still be waiting for input on that file. It won't actually stop trying to read if there's an open file still there. So you can see here, I don't get my command prompt again. It says hello, and the child process is still running, waiting for input from the parent. So you can see both are running now because I've waited for the child here. But if I didn't wait for the child, I could just quit, and the child will be stuck waiting for that file to close on the parent side. So here's another example of it. Oh, actually, okay, so it closed when anyway. So if you don't call close, then the child will still wait for that input. Okay, other questions? Other questions on this? So these are more sort of minor things. These are tricky things to get right, but if you notice in your shell, and I'll talk about this next time, if you notice in your shell that your shell is hanging, then it's probably could be because of this. But I'll cover that next time when we actually go over the shell exercise. Other questions on this? Other questions on this? All right, so let's do the last example. The last example is basically combining redirection, fork and exec, and pipes all together to see how we can implement this, see how bash implements this simple looking command, but using all of these syscalls together. Okay, so the way it's going to work is we're going to have one sort of master process, a parent process, and I'm going to call this program filter. And this is going to create two new processes. It's going to create a process to run ls. It's going to create a process to run wc. And this is not necessarily the order, but it'll create a pipe, fork these two processes, redirect the standard out of ls to the pipe, redirect the standard in of wc from the pipe, and then let these programs run. Questions on this setup? So this is sort of our master program. It's going to call pipe here. It's going to call fork for these processes. It's going to call dupe2 for this redirection, and then it's going to call exec on, and that's going to just let these processes run. So this is going to be, it's going to call exec eventually. So as we saw last time with redirection, you have to first fork, then do the redirection with dupe, then call exec. But this is just sort of overall diagram of how this setup is going to work. So questions on this setup? All right. All right. Let me just go into the actual code here. Okay. Yeah. Actually, this is actually kind of useful. Pseudocode. So getting the order of this stuff is tricky, and it's tricky to get right. And there's some subtlety in doing this. So we create the new pipe, and we want to do that before we fork because we want that pipe to be accessible by both children, by both child processes. So remember, if you fork, you get all the open files copied. So we call pipe first. Then we fork the left child. So we have code to check whether they're in the child. In the left child, we close the read end of the pipe, and we redirect the right end of the pipe with standard out. So instead of standard out, this process is going to be writing to the pipe. Questions on that? So we create a new pipe in the parent, we fork the left child, and we do a redirection. We redirect standard out, and then exec the actual program that's going to run. Questions on that part? So this is what we did last time, redirection. So this is the code for redirection. So you fork the child process, call dupe2 to redirect standard out, and then exec the program. Only here, instead of redirecting to a file, we're redirecting to the pipe that we created. Questions on that? Questions on that step? Okay. For the right child, once we fork, the parent can continue executing. So in the parent, we're going to call fork again for the right child. And here we're going to do the same thing, but instead of redirecting standard out, we're going to redirect standard in. So we're going to take the other end of the pipe, the read end of the pipe, and we're going to redirect standard in to that pipe. And finally execute WC, the right program. And then we're just going to close the pipe in the parent and wait for the two processes to finish. Questions on this pseudocode? Not too bad, right? Pretty straightforward, yeah.
Is it running in somewhere as well?
Well, remember with fork, when you create a new process, the kernel decides the scheduling. So these code snippets inside of the child, these are running asynchronously from each other and from the parent. So as soon as you call fork, it's asynchronous. Questions on this? So hopefully this looks somewhat familiar. So this is just redirection here with fork exec. This is redirection with fork exec. And the only real difference here is that, we're creating two children and we're using pipe for the redirection instead of opening a file from storage. Questions on this before we see the real code? So this will help understand what the C code is doing because it's a little bit longer. All right, let's take a look at the actual program. So there's documentation, and here is filter.c. Okay, first thing we do, create the pipe, just like we saw in the pseudocode. Then we fork. So here's the code for fork. We call fork. Case 0 is the child. There's lots of error handling, which is why the code is a little more verbose. We close the read end of the pipe, just like we saw in the last example. And then here, we redirect standard out for this new process we created to the right end of the pipe. We close the other end of the pipe because we close the right end of the pipe because we've duplicated it. We don't need that open file descriptor anymore. And then this code here is what we saw last week on how to run exec. So we're going to run the find program with user bin as its argument. And this is where we call exec. Questions on this code? So it's just like we saw with the pseudocode. Create a new process, redirect standard out to pipe, and exec find. Questions on this? So back in the parent, there's nothing to do here. We just want to move on and fork the right child. So at this point in the program, because exec is guaranteed not to return and we have an exit here, at this point in the program, we must be in the parent process. There's no way to be in a child process at this point in the program. So same thing, we call fork, and here we are on the right-hand side of the child. We close the in side of the pipe, the right side of the pipe, because this is the child that's going to be reading it. And here we redirect standard in. So now standard in is coming from the read end of the pipe. We close the pipe file descriptor because it's already been duplicated. And then same as the other child, we just call grep here. So this is the input to exec. It calls grep with the argument zip, and we exec it. Questions on this side? And then back in the parent, we close both of the pipe file descriptors because if we leave it open, then the read end will be blocked waiting for that file to close. And then we just call wait. So the parent will just run until both children have finished running. Questions on this? Questions on this code? So I know it's a little, it's probably a lot to look at just on a screen, but let's see it actually running. Hopefully it'll work. Okay, so hard to see what's going on here, but if I run these programs individually, there's find with grep zip, and you can see this is the output of these piped commands. And it's the same as when we run our filter program. So our filter program has done the exact same thing effectively that bash has done. And this is what bash actually does under the hood to make this possible. Questions on this? All right, so let me diagram this again just to make sure we're on the same page with the code. So I'll diagram this like more in the order that we see it in the code. All right, so we run the filter program. We have one process, the filter process running. we call pipe, and this creates a new in-memory buffer. The kernel creates this for us and gives us two file descriptors. The read end, which is 0, right? And the write end is 1. And what's the next thing we do? We call fork. So when we call fork, we have a duplicate filter process. And all file descriptors are copied. We call dup2 so that standard out is now redirected to the right end of the pipe. And then we call exec, which is going to replace filter with find. Questions so far? So that's all this code does in so far. Now, we called fork, and in the parent process is still running. The parent process will continue to run fork for the right child. So this process runs fork for the right child, which creates a duplicate of the filter process at this point in its execution. And then we call dup2 to redirect standard in from pipe FD0. And then finally, exec is used to replace this process with the grep program. Finally, back in the parent closes access to these file descriptors and then calls wait to wait for these processes to finish. Questions on that? I know it's a lot of steps. It's combining a lot of the API that we have, but hopefully that diagram kind of helps to see what it's doing conceptually. Questions? Yeah. Dup2 is for redirection. So let me show an example here. So before we call dup2, what I didn't kind of fully write here. So we call fork, and the first time when we call fork, a copy of the filter process is made. So filter has standard I/O already. It already has a standard out and a standard in. In our case, it's to the terminal. So when we call fork, standard out and standard in are copied because all open file descriptors are copied. So standard in and standard out are copied. When we call dup2, we're taking out and we're changing that file descriptor for standard out to be the same open file as the input side to the pipe. That's what dup2 is doing here. And same on the other side. So I didn't fully flesh out all the I/O here, but that's what dup2 is doing. It's replacing the standard out file descriptor, which on my system is file descriptor 1. And dup2 will delete that entry, which is, makes it not possible to write to the terminal anymore. And then it'll replace that with an existing open file descriptor, in this case, the right end of the pipe. And then once that's done, we call exec, and that will replace the filter program with the find program. And once we call exec just starts running, and exec just starts writing immediately to this right end of the pipe. Even if that starts before exec runs, it doesn't matter because it's being buffered by the kernel. The kernel will, even if that buffer fills up, find will be trying to write to this pipe, but it's blocking. It'll wait until it can successfully finish a write. And once grep gets forked and running, it'll start reading from this pipe, and the kernel will allow the write to continue once the buffer has been flushed out, once it's been read. Other questions on this? Other questions on this example? Yeah.
The parent in this case, is like quote unquote using the pipe. If they don't close the right end, will the program still hang?
Yes, yeah. The parent, with the parent having it open, then this child process, this grep, will still be trying to read because it's an open file. So the kernel won't terminate the read. It won't terminate the read instruction until that file is closed. So yeah.
So if those prices copied into the child process have to be individually closed and also read.
Yeah, that's right. Yeah, exactly. So that's some annoying bookkeeping to keep track of. But this, if you look at this example, it shows you like a full example of that. And yeah, next week I'll go over the next project, which is actually going to be implementing a bash-style command processor. And you'll be taking in input. So instead of writing one program that just says find and grep, you'll take an input from the user and construct pipes and redirection for any program that's given to you, just like bash does. And so yeah, you'll have to be careful, kind of meticulous about making sure the file descriptors are closed. Yeah.
I'm kind of confused on like, if you tell, like, if you send a program in the bash, it will automatically put the pipes in, like, to figure that out.
Yeah.
Okay.
Yeah. It'll, yeah.
That's when you're passing in like things that require the pipes, right? Not like a program that doesn't have the pipes. It won't like automatically have the pipes to make it more.
No, it does it when commanded to. So if you say ls this, so when you put a pipe symbol, that's when you're telling. It's like when C, when you write code, when you write a plus symbol, you're telling the C language processor to do an addition. It's the same thing here. You're telling bash to create a pipe and do the redirection for you. And we'll talk about that next time. This will be like an intro to kind of language processing. We'll do a little intro to language processing, and then you'll use what you learned here to actually implement a command line processor that uses do, fork, etc. All right, everybody. If you have any other questions, come up and talk. And otherwise, have a good week. See you next week.